So today we will see about control rectifier. This is part 2. If you want to see part 1, link is given in the description. So already we have seen about half-wave rectifier feeding RL load. The main limitation of this circuit is that inductor current will not become zero at pi. It continues to flow even after pi. So this thyristor will be conducting even after pi. So net effect is that your output voltage will have a negative part, and if I find the average value for this voltage equation, it get reduces because of this presence of negative part. And moreover, due to this, the efficiency of the system will be lower and the load performance is poor. Now, how can we remove this negative portion so that your average voltage increases? So for that you can use a freewheeling diode. So by providing a freewheeling diode, what you are doing, you are removing this negative part. So in this video, we will be seeing about half-wave rectifier feeding RL load with a freewheeling diode. So this is the circuit with freewheeling diode. So during positive half cycle, what happens? So here it is positive, here it is negative. So this thyristor is forward biased and current flows through the load in this direction. At this time, that is during the positive cycle, this freewheeling diode will be reverse biased because it is connected to negative here. And during negative half cycle, here it is negative and here it is positive. So thyristor will be turned off and this diode gets forward biased. So current flows through this way. So in this method, what happens? Now output voltage V0 is directly in parallel with the diode. So diode voltage is almost 1 volt, or you can take it as a very low value. So V0 is directly shorted. So V0 is equal to 0 in this case. So here V0 is equal to Vs, and in the negative half cycle V0 equal to 0. And this inductor current continues to flow in this path till all the energy stored in the inductance is dissipated in the resistor. So we have seen positive half cycle. So current flows through the load and you will get the load voltage is equal to supply voltage during past half cycle. So alpha to pi, you will get the voltage as V0 is equal to supply voltage Vs. During negative half cycle, output is shorted by the diode. So output voltage is 0. So you can see output voltage is 0. Now you have to see the current. So if you see the load current during past half cycle, it continues to increase. So it continues to increase, and during negative half cycle only this freewheeling current flows. So current starts to decrease. Okay. So this type of waveform is called continuous current. So this occurs when this inductance L is a higher value. So when L is higher, current will not become zero anywhere. Instead, it continues to flow. But when L is a very low value, you may get a discontinuous current. So in that case, waveform will be, that is, it will start from alpha increases, then during negative half cycle it decreases and becomes 0 at beta. So this is beta. After that it remains 0 till 2 pi plus alpha, then again increases. So in this case we call this current as discontinuous current. So this load current can be continuous or discontinuous depending upon this load parameters R and L. Now we will find the average value of the output voltage. So we can say what is the limit for output voltage? Alpha to pi. So total time period is 2 pi, limit when is alpha to pi. So substitute V naught equal to Vm sin omega t, integrate it, you will get Vm by 2 pi into 1 plus cos alpha. Now we will find how to draw this voltage across the thyristor waveform. So it is a rule that whenever a device is conducting, voltage will be 0. So alpha to pi it is conducting, voltage is 0. Remaining times follow the input waveform. So 0 to alpha follow the input waveform, this one, and for pi to 2 pi plus alpha again follow the input voltage waveform. So this is easy. And here one more term is given, omega tc. This is called circuit turn off time. That is the turn off time provided by this circuit, or for which period it remains reverse biased. So this circuit turn off time tc is equal to pi by omega c, because this period is pi, so by omega c. Then we will find the RMS voltage. So limits is alpha to pi. So you do the calculation. This is the RMS voltage. So now we have seen about the effect of freewheeling diode. That is, you can see that there is no negative portion in the output voltage. So average value increases and efficiency will be improved as the energy stored in the inductance is delivered to the load again, and current has a smoother waveform, so load performance will be better. Now we will see the next circuit, half-wave rectifier feeding RLE load. So we have seen about RL load. Here you have one more parameter E. This is the battery. So this E can be a battery or the back EMF of a DC motor. It can be anything. So it depends upon the application. So to study this circuit, you need to understand some basic waveforms. So this is the circuit, and let me draw the supply voltage waveform, and this blue color line represents the E. So here you have Vs and here you have E. So Vs is connected to this side of thyristor and E is connected to the other side of the thyristor. So this thyristor, when it will be forward biased, whenever Vs is greater than E only, it will be forward biased, and after that if you give a gate pulse, it will get turned on. Now let me apply a gate pulse here. So you see here, so I have applied a gate pulse at this point. In this point, this Vs, this brown color line is Vs. This Vs is lower than the back EMF E. So Vs is lower. So thyristor, though I give a gate pulse, it will not conduct because it is reverse biased. So output voltage will not be there. Output voltage will be equal to E. This is not conducting, so output voltage will be equal to E. So I can get only E as output in this case. Now I can give a gate pulse here because at this junction Vs is greater than E. So when you give a gate pulse after this junction, Vs will be greater than E. So if a gate pulse give a gate pulse at this point, it will start conduction. So after this, it will follow SER conducts and it follows the input waveform. Now if I give a gate pulse here, what happens? So this point is after this junction. It means that Vs has become lower than E. Again at this point SER will not conduct. So I can give a gate pulse here or here or here or here. So within this range I can give the gate pulse. I cannot give a gate pulse after this because SER will not be forward biased. So SER remains forward biased only within this range. And what is the minimum value of alpha you can give can be found from this equation. That is Vs is equal to E. So this junction point you have to find what is the alpha value. So Vm sin theta 1 equal to E. From this you can find some theta. Suppose this value is around 30 degree. Always make your alpha greater than 30 degree so that SER will conduct. Now let us see about the output voltage waveform. Here you can see that this alpha is given after theta 1 so that the device will be forward biased and it starts conduction. You should not give alpha below theta 1. In this range you cannot give alpha. Okay. Now when the SER is in off condition, output voltage V0 is equal to E. So V0 is equal to E. Once it starts conduction, it will be equal to the supply voltage. So follow the supply voltage till this point. So what is this point? It is the beta point or the point at which current becomes 0. So till that SER conducts and it will follow the supply voltage waveform. Remaining time it will be equal to this E. So the conduction period of the SER is only this range. Okay. So this theta 2 you can write it as pi minus theta 1 because both values will be same. Theta 1 will be equal to theta 2. So theta 2 you can write this pi minus theta 1 minus of this value. So this will give you this range theta 2 minus theta 1 value. Now let us find the voltage across the thyristor. Vt is equal to supply voltage minus load voltage. For load you have IR plus L into di by dt plus E, but L into di by dt is equal to 0 because voltage across the inductor will always be 0. So let us apply the boundary condition at omega t equal to 0. Supply voltage is 0. So 0 minus E and I0 value is also 0. So substitute that you will get minus E. So you can find here it is equal to minus E at this point. Then you can find what is the value at theta 1. So at theta 1 supply voltage will be equal to E. So E minus E. This I0 is again a 0 value. So 0. So Vt is equal to 0. So you can find this at theta 1 Vt is equal to 0. Next, at omega t equal to 3 pi by 2, what is Vt? So Vs is equal to minus Vm at this point. So minus Vm minus E, and I naught value is 0. So you will get minus Vm plus E. So we are finding the boundary condition only for certain angles, because for the remaining period we know that when the device is in conduction, the voltage across the thyristor is going to be 0. So no need to find for these things, it is already 0. So now let us find what is the value of beta. This has been already derived in diode rectifier, same type of equation, except that you will get one more term E. So this is V naught is equal to Vs. So in that you will, if you solve it, you will get this one. You have to find the value of A, apply the boundary condition at omega t equal to alpha and I naught equal to 0. You can find the value of A. Then substitute it in this equation, you will get I naught. Again you have to find at omega t equal to beta, I naught equal to 0. You can apply that and get one equation. This is not easy to solve manually. You can do some programming to solve this equation. But for a theory point of view, you can stop with this. Now we will find the average voltage. So this is the waveform. This is a little bit different from the previous waveforms you have seen, because you will have one more term E. So you have two limits. So total time period is 2 pi. So you see the waveform from alpha to beta, your output voltage is equal to Vm sin omega t. From beta to 2 pi plus alpha, it is E. So E I have written here, you can write inside also. Okay. So instead of taking 0 to alpha period, I have taken 2 pi to 2 pi plus alpha. So this side I have taken. You can take in any way, you will get the same result. So if you solve this, it is very easy, you will get this equation. So the points to remember here are, in a controlled rectifier, the load voltage is controlled by controlling the firing angle. Load current can be continuous or discontinuous depending upon the load parameters R and L. And the presence of a freewheeling diode helps to improve the load performance and increase the average output voltage. These are some of the references. If you like the video, do subscribe to our electric vehicle channel. Thank you.